can share your
Okay.
screen.
Yeah. So screen is visible, right?
Yeah.
Okay. I will start with an example actually, then we'll
Mm-hmm.
come to this part. Easier to explain. So Prim's algorithm is also similar to Kruskal's algorithm, where we are trying to find a minimum spanning tree. Only
Mm-hmm.
the approach is different. And minimum spanning tree we already know, which covers all the vertices, and sum of the weights of the edges should be minimum. So that is the minimum spanning tree.
Okay, just sorry to interrupt you 1 second. Uh, where did the Kruskal's algorithm go in the
Oh, sorry, I
text?
moved it. I moved it adjacent to Prim's, so I think they are related. So I just moved it.
Can you like later on just move it back there because I'm trying to keep all the blue sides together so that we don't miss on to the daily revision.
Okay, okay, okay. Okay, I will move it back. Sorry.
And guys, whoever is editor, please be very careful. Don't end up deleting it accidentally. Uh, yeah,
Okay,
let's
okay,
continue.
okay. So let's start with an example, or let's go through the steps basically. Then we'll see the example. So first
Mm.
we have to initialize an MST. MST is minimum spanning tree
Correct.
with randomly chosen vertex. We will choose any vertex randomly and we'll start with that. Now we find all the edges which are coming through this vertex, and we uh, add the minimum edge to the tree. So out of all the edges, we select the minimum edge and add it to the tree. The edge whose weight is minimum, will add that to the tree, and then we'll keep repeating this step 2 until the minimum spanning tree is found, which means all the vertices are covered, until all the vertices are covered.
So is it
So
not same as organizing it in ascending order?
no, it's a
How is
little
that different?
different.
Yeah, picking up the smallest one.
uh, because we are picking the smallest from a particular vertex, not smaller from all the edges. Like if we start with C here, for example,
Hmm.
then the minimum can be 2, 6, 10, or 3.
Okay, so
But
all the edges that are originating from that particular node, we
yes,
have to consider the smallest out of those,
yes,
and then we
exactly.
can start from anywhere.
Yes,
Okay.
as is written, we can start with the randomly chosen vertex.
Mm-hmm.
So let's say we consider this graph, for example. This is a weighted graph, and the weight is mentioned here. We start
Okay.
with a vertex B, let's say.
Okay.
Okay. And if we see in this graph, there are two edges which are coming from B. One is 4,
Four is the
one is
smallest.
10. Yeah. So in these edges, 4 is smaller. So since 4 is smaller, we'll add this edge to our MST and we'll add this vertex also.
Yep.
Okay. So and we'll add the weight of this edge BD to our weight of MST.
Of
Okay.
course.
So weight of MST becomes 4 now. So now again we choose the edge with the minimum weight. Okay. And now we so let's say if we have this subtree, or uh, yeah, we have this subtree. Now we can choose all the edges which are coming from any of these two. Okay.
Mm-hmm. So we
So
can either choose B, we can either start from B again, or we can start from D, but it doesn't make sense to start from B because we don't really have any other smaller one than that.
no, we cannot. It's not either or. We have to make a combination of. So let's say if we have this BD, we have already considered this edge. Now we consider all the edges which are coming from B and which are coming from D. So from B, this 4 is already covered. Then there is 10. and from D there is 2 and there is 1. So between 1, 2, and 10, we have to choose the minimum.
Oh,
Yeah.
that's gonna start getting complicated as it grows, then, wouldn't it?
Um,
Because as we progress further, we're gonna have more nodes, so now there'll be more choices.
and let me check if it's correct, or we have to consider only the edges from D.
Mm.
So we added this one, then this one. Yeah, I think what I mentioned is correct.
You have to consider everything, both B and D.
Yeah.
So then, after E comes into picture, we'll have to consider all three, B, D, and
Yes.
E.
Yes.
So what is smaller? Uh, give me the edge that's connected to either of this, which is the
Yeah.
smallest.
Yes. Exactly.
Okay.
So we go through an example, then we'll see if there are any questions. So we start with
Okay.
B, and the smallest edge is 4, between 4 and 10. So we add this edge to minimum spanning tree, and then we see all the edges from B and D, which are 10, 2, and 1, out of which the smallest is 1. So we add this one, 1, to our minimum spanning tree. And now we see all the edges from B, D, and E. So if we see in the graph from B, D, and E, which are not already in the MST, of course, then there is 10, 2, and 6. Out of 10, 2, and 6, the 2 is minimum. So we add it also to MST. And then these four vertices are there now. Now we have to check all the edges which are from all of these four vertices, minimum of the edge. And if we check again, there is 6, there is 10, there is 3. So I think the minimum is 3.
Hmm.
So then we add the edge, which is the minimum again, which is 3. Now if we consider this subgraph, this has all the vertices covered, so this can be called a minimum spanning tree. And the weight of minimum spanning tree will be 4 plus 2 plus 1 plus 3, which is 10.
Okay. So the idea about minimum spanning tree is that all the vertices should be covered, and none
Yeah.
of them should form a cycle.
Yeah.
Correct.
Yeah.
Okay.
And
That's
while yeah, that condition is same in crustals and prims. So while adding an edge, we should see that it is not forming a cycle.
okay.
That is not written here, but yeah. Is this
Okay.
example clear, or shall I go
Yeah.
through it
Yeah.
again?
100%. I mean, I can recap that. If you want.
Yeah, would
So
be great.
basically, what we do is go up.
Yeah.
Yeah, basically what we do is just pick up any point, and from that point, you have to see what all edges are originating. Like, let's say if I pick up B, and we have 10 and we have 4, that's originating. And we have to choose between which one is the smallest. So let's say 4 is the smallest. So we have to write both the nodes, which is B and D, which uses 4 basically. Once we do that, then we need to see which are the nodes which are now present in our current structure. So current one are B and D. So we have to now check all the edges that originate from B and D, and we have to compare the smallest one which is not already present, and then place that, and we just have to keep following this step until unless all the vertices are present and we don't form a cycle. Any case it's forming a cycle, we will go ahead and skip that.
Yeah. And I think if we start
Yeah.
from any vertex, the output will be same.
Yeah.
And output of prims and crustal is also same, because they are basically calculating the same thing.
Okay, sounds good. Just let's look at the content that you pasted on the
Yeah,
slides.
sure. So basically, go
This is
to
Prism.
prims. Prims algorithm is a greedy algorithm. Greedy means basically, in simple language, greedy means choose the minimum.
Okay.
Uh, Prims
If
algorithm
it's
is a
greedy,
greedy.
then how is one is choosing the minimum? I should be choosing the more, right? Somebody who's greedy will take more, not less.
Uh, yes, it depends on the case to case basis. Sometimes it's minimum or sometimes it's maximum, but it's usually one of them. So different scenarios, greedy is different, basically. Yeah.
Okay.
In terms of money, greedy is more, but in terms of other things, greedy can be less.
Okay. Okay. Just give me 1 minute. I'll be back. 1 minute.
Sure.
इस केस में अगर हम
Okay, I'm back. Let's continue with the next one.
Yeah. So we're at the slide, right? So Prim's algorithm is a greedy algorithm that starts from one vertex and continue to add the edges with the smallest or weights until the goal is reached. Smallest weight is
Mhm.
until the goal is reached. Goal is basically a minimum spanning tree is created, or until I will simplify this until MST is created. Yeah. So the step these are the steps of the algorithm. Step one is select a starting vertex. It can be any randomly chosen vertex. And then step two is basically keep repeating steps three and four until there are fringe vertices. Fringe vertices are basically disconnected vertices, you can say them. So I will write disconnected as well. So which are not connected in the MST or which are not connected in the graph right now. So until any disconnected vertices are there, we should keep repeating step 3 and 4. And in step 3 and 4, what we are doing is basically in step 3, we are selecting an edge connecting the tree vertex and a fringe vertex that has minimum weight. So if we go to the example again, so right now, if we are at B and D, then uh, so these two are tree vertices or MST vertices, and rest all the vertices are fringe vertices. Okay. Now we have to select any edge from these tree vertices to fringe vertices whose weight is minimum. That's what it says in the algorithm as well. Is that clear? Select an edge connecting the tree vertex and fringe vertex that has minimum weight.
Okay.
So in this step, BD was our tree and the rest of the vertices were fringe vertex. So we found an edge. We add it to MST and then add the selected edge and the vertex to the minimum spanning tree only if a cycle is not created.
Mm.
Okay. So that is the basics of the algorithm. And the application of the algorithms are in network designing, network cycles, and to lay down electrical wiring cables. So they are similar to Kruskal's, I think.
Okay. Why are they called disconnected vertices? Step two.
Disconnected in this example, basically, so they are not connected to our MST that we are trying to form.
Mhm.
So connected or disconnected vertices in graph usually means if any vertex is connected to the graph via any of the edges, that means it's a connected vertex. And the disconnected vertices are whichever are not connected. So right now, we consider this as our MST, then all the other vertices are disconnected or fringe vertices.
They are disconnected to the one we have at the bottom,
Yeah, they're
right?
disconnected to the MST that we are creating.
Yep. That's what I thought.
Yes. And I've tagged you that I think if we can delete this or we should keep it because this is a bit confusing, I think.
As long as the one we have is correct, it's fine to ignore the one in the screenshot.
Yeah. Okay. Okay. So is this clear? Shall I repeat or shall I move forward
No, no,
to the
let's
next?
move to the next one. Does anyone else have any question? Okay, let's move on. Next one.
Okay. Next one is Dijkstra's algorithm. Hmm. So we'll again start with an example, then come to the algorithm again. Hmm. Okay, we'll go through the basic steps of the algorithm and then we'll see the example. So
Hmm.
basically, we create a shortest path tree set. This is similar to the MST we were creating. So this is called the shortest path tree set. And sorry, to introduce the Dijkstra's algorithm, it is used to find the shortest paths from a source vertex to all the vertices in a given graph.
Hmm.
That is the use of Dijkstra's algorithm.
Okay.
So we create a shortest path tree set which keeps tracks of vertices which are included in the shortest path tree.
Hmm.
Basically, it's a set in which all the vertices which I have already covered, they will be added to this set. Okay. Then in the beginning, we'll assign a distance to all the vertices in the input graph, and we will initialize them as infinite because we want to calculate the minimum. So we assign them the max value, which is infinite, or we can use integer dot max value here as well, and assign the distance value as 0 to the source vertex because we are starting with the source. So to reach the source, we don't need any distance. We are already at the source, so we'll assign it as 0 distance.
Hmm.
Then the next steps are while the shortest path tree set is not created, while it doesn't include all the vertices, which is the same as MST, while it doesn't include all the vertices, pick a vertex U, which is not in the shortest path tree set, which is not covered already basically, and has a minimum distance value.
I think we'll
So
understand better with the example because by
yeah,
just looking at the content, it's not very clear.
yeah, I'll go through an example then. Okay, so let's say we have this graph and our source vertex is 0.
Club is just too much.
We can take any graph, like if we have only 4 or 5 edges, that's also fine. It doesn't make a difference, I
Yeah,
would
just
say.
too big. Anyways, let's move on.
Yeah. So if we start with source vertex as 0, then it has 2 edges. Okay. Uh, so in this, we don't choose minimum as we were doing in Prem's algorithm. What we do here is we update the distance of both these edges or both the vertices. Okay.
How do you calculate the distance?
So distance calculation formula I will show you. So calculation formula will be distance of my source vertex plus the weight of this edge. Okay. So distance of 0 is 0 and this weight is 4. So if this
4 plus
plus
0,
this, what?
4 plus 0 and 0 plus 8. Correct?
Yeah. So 0 plus 4 and 0 plus 8. If this distance is less than the current distance of the target node, right now its current distance we have initialized with infinite. Okay. So
Sorry,
distance
that.
of every node we have initialized as infinite. So distance of 1, distance of 8, all the nodes which are in the graph are their initial in their beginning, their distance will be infinite. Okay. Hello.
No, didn't understand.
Uh, so in the beginning, we are creating a distance array, let's say. Okay. And in the final output, we have to output this distance array. Okay. In the
Okay.
distance array, we want to store the distance of every vertex from our source vertex. Okay. So in this distance array, this is the array. We have initialized this array as 0 for the source vertex, and for every other vertex, I have initialized the distance as infinite. Because
Okay.
I don't know what their distance is, I want to calculate the minimum distance, so I want to assign a max value in the beginning.
So initially they are infinite except the first one.
Initially they are infinite, yes.
Okay.
Okay. So now if I calculate the distance for this node from this node, so distance of source is 0, and distance of target will be distance of source plus weight of this edge, which is 0 plus 4. So if 0 plus 4 is less than their current distance, which is infinite, so it will be definitely 4 is less than infinite. So we will update this distance. Okay.
Understood.
Only if it is less, then only we'll update. That is the crucial point.
Okay.
If it's less than their current distance, then only we'll update the distance.
Understood.
So in this example, in the beginning, anyways, everything is infinite. So we'll update as 4 and 8 here. then we then now 0 is added to my shortest path tree set. Okay, SPT, which is called here. Okay, 0 is already added. Now I come to 1, and now I update the distance of all the vertices which are connected to 1. Okay,
Oh,
in this graph, 2 is connected to 1 and 7 is connected to 1. Okay,
yeah.
so what should be the distance of 2? It should be distance of 1 plus
Wait, wait.
this weight.
No, I think it's 8 plus 4, 12. You see that?
Yeah, that's what I'm saying. So it should be
No.
distance of, now distance
In
of
the
1
current,
is updated to 4 now. Okay,
yeah. So
after
current
this step.
situation, if you scroll down
Yeah,
in the current graph,
in this
we,
graph.
yeah, in this graph, the
Mm-hmm.
distance of 2
Mm-hmm.
is, I think, 0 to 1 and 1 to 2, which is 4 plus 8.
Yes.
I think that's how it's calculating from the main source, the original source, because other sums don't match and don't count up to 12.
Yeah, you're right in a way, but we don't need the distance from the source because we already know the distance from the source for 1. We already calculated it and we have stored it, so we can use it directly.
Oh, okay. Yeah, 4 plus 8 then.
Yeah, 4 plus 8. We already know the distance of 1. Now then we from 1 to
Yeah, that
2.
makes sense.
Yeah. So now the crucial point is we have updated this distance, but we have not updated this distance.
Hmm.
And I will tell you the reason behind it. If we calculate this distance of 7 from 1, it will be 4 plus 11, which will be 15. And its current distance is 8. So since 15 is greater than 8, we will not update it. We will only update if the distance is
But we
less than
can't
the current
match it
distance.
anyways, right? Because it's going to form a cycle.
Sorry, can you repeat that?
Yeah, it's going to form a cycle if I connect the 7 with 1. So we shouldn't be connecting anyways.
Uh, yeah. Yeah, that's true, but I'm not 100% sure if Dijkstra's, if we can have cycles or not. I think we cannot. But again, that is another example. If there was no cycle also, then
Yeah,
again, this condition is the critical condition basically.
understood.
So
My question is that why did we choose 1 as the next source? So is it that after the first step, whatever nodes we have available, we are going to
mhm.
start from there? How did we decide we are supposed to choose 1 after 0?
So after 0, we can either choose 1 or we can choose 7.
Okay,
Okay. Both will work. Both will work the same way. The solution will be fine. But
okay,
we can only choose the vertex which are connected to 0 basically.
okay. So now are we going to choose 7?
Wait a second.
Since
No,
1
no,
is
no.
done.
Sorry, I was wrong. So we have to pick the vertex with minimum distance value. Now here, after adding this, the minimum distance value is 4. So we have chosen 1.
Okay,
So as if mentioned here, we have to choose the vertex with minimum distance value.
okay.
That is not in our set. So
Correct.
in this graph, out of 4 and 8, minimum distance is 4. So we have chosen 4. And
Now
now
in the
again,
next
if
step,
we
it's going to be 8 because 12
will
is
choose,
higher.
yes, yes, exactly. So we'll choose 7, and then we update the distance of the nodes which are connected to 7, and similarly will continue basically.
Hmm.
Now, if there is one interesting point, so if you see the distance of 8 is marked as 15 now. Okay,
Hmm.
hello.
Yeah, yeah.
But if we traverse 15 from this second node, I think it's connected to second also, then the resultant distance will be less than 15. It will become 14. Okay. So since the distance is less, then we will update the distance to 14
And remove the connection.
and remove the connection.
Hmm.
Is this clear, or shall I go through step by step again, once again?
I'll recap this for you. Tell me if it's
Yeah,
correct.
yeah, sure.
So there are two key things we have to remember. How we're going to traverse, like what nodes are we going to pick up, and second part is calculating the distance.
Yes.
So initially, we can start from anywhere, right?
Yeah, we can start from any.
Okay.
Usually, the source vertex is given in Dextras.
Okay, no
Yeah,
problem.
given a graph and source vertex is given.
Fine. So let's say we start from zero.
Hmm.
So first question is, uh, how are we gonna traverse? So right now we don't have to worry about traversing. Right now we just put all of the nodes that are connected to our source, whatever we have chosen. In this case, there were two of them. There were 1 and there were 7. In order for us to calculate the distance, it'll be um, the distance of the source node plus the distance plus the edge value, whatever the weight of the edge value is.
Yes.
So in this case, it's 0 plus 4, so 1 becomes 4. Similarly, 0 plus 8 becomes 8.
Yeah.
Don't get confused by the number there, uh, like 1 and 7. They are not related to what you see on top, which is the distance. Distance is different than that.
Yeah.
Now, how do we go next? So the rule for going or picking up the next set of vertices is you check those adjacent nodes, or if there were two or three. In this case, there are two of them, 1 and 7. So how to choose, where to go next? So basically, we'll check which whose distance is smaller. So in this case, one's distance is smaller, which is 4. That's why we pick it up. Again,
Yeah.
we follow the same rule which we followed earlier, and we are going to reach to 2, and the calculation formula was the distance of the source, which is 4,
Yeah.
plus the weight of between 1 to 2, which makes
Yeah.
a total of 4 plus 8, which is 12.
Yeah.
And now between 2 and 7, the smaller weight is 8, so we pick up 7 and then we traverse.
Yeah.
Now there will be some twist which you spoke about if you scroll down.
Yeah.
Yeah, so sometimes you'll notice that at number 8, okay, uh, the weight of 2 is 12, and I think 8 is 15. So you can't complete a cycle, I think, in this case also. So you have to choose between which connection you will choose between 2 to 8 or 8 to 6. So depending on which
Yes.
one is smaller, I guess we are choosing that one and removing the other one.
Uh, yeah. So basically, what is happening here is as we are iterating over one vertex by one. So we came to 0, then we came to 1, then we came to 7, then we came to 6. When we came to 6, we updated the distance of all its adjacent vertices. So distance
Hmm.
of 8 is also updated. Now after that, what will happen is we again choose the minimum distance vertex. Now it will be 5. Okay, because the distance is 11, so 5 will be included and distance of 4 will be updated here. Then after some point, this will be chosen, 2 will be chosen. After 11, the distance of 2 is 12, so 2 will be chosen. Now 2 will try to update the distance of all its neighbors. So the neighbor of 2 is 8 and 3. Okay, so it will try to update the distance of 8 and 3. So if it
Hmm.
calculates the distance of 8, the current distance of 2 is 12, and this is This weight of this edge between 2 to 8 is 2. So 12 plus 2 is 14, which is less than its current distance, which is 15. So distance of 8 will be updated. So minimum distance of 8 from 0 is 14. It's not 15.
Hmm.
So that's why it is updated.
Yeah, it's really, if you ask me honestly, it's just too confusing. I don't know why they create such complex algorithm. They're trying to. Anyways,
Yeah, it is one of the tough ones, I would say.
hmm. In exam we have to find out a smaller example because there's too much going on there.
I think we can, instead of this, we can have just four nodes,
Yeah, that's
and
it.
then we can just, yeah, that should be
Like
sufficient to explain.
exactly. Like remember we did first depth search where we just have few nodes and we were done. Similarly for this also. The more complexity we add, difficult it will be there in exam. Anyways,
Yeah,
does anyone have any questions?
I think then this would be self-explanatory kind of.
Yeah, that's fine. Let's leave that. Uh, do we have any other algorithm we were supposed to discuss?
Yeah, there is Bellman Ford also, but I couldn't get a chance to understand it
That's
completely.
fine.
So
That's fine. Let's
I,
leave that for now.
I think that is too much more complex than Dextra's also. So not sure
Then
if we
leave
should
that.
cover it.
We'll not do it. I mean, whoever wants to do it, you can do it. Feel free. But yeah, as a group, we won't do it. I think this is enough. Uh,
Yeah.
so Anirudh,
That
what
one
else?
is not there in the syllabus also.
Oh, that's great. Did I then add? I shouldn't have added that in the list then. Anirudh.
Oh,
Bellman
was it
Ford
there? I didn't come across it.
is
What was
there.
the name?
There was something mentioned that graph with negative edges. Yeah. Uh, so in shortest path
CL.
algorithm, graph with negative edge cost is mentioned. So that
Yes,
uh,
graph with the
that
negative
is
edge.
the
Yes,
so
it's there
that
in
is
the
the
syllabus.
Bellman Ford algorithm actually.
Okay,
So
okay.
basically, it's Dijkstra algorithm. If in Dijkstra, if it has negative edges, Dijkstra doesn't work. So that's why there is a new algorithm, but that is
What
too
about
complex.
acyclic graphs and all pair shortest path algorithm? There are two more.
Uh, that also I didn't find the time to
That's
cover those,
okay.
but I think I can cover maybe the third and fourth one, but negative edge cost is too complex.
Leave the negative. Whatever the simpler one are, you think we can cover? Can we cover that tomorrow?
Yeah, yeah, sure.
Okay, excellent. So yeah, we'll stop here. Let you guys take some rest, and we'll start again at 9:30, and we'll do Java because hardly we have time. We just have 2 more days, tomorrow and day after. So yeah, tomorrow we'll be preparing just the DSA, and day after will be just the uh, Java. So yeah, let's meet at 9:30 between, and we'll try to wrap it up by 11:15. Okay,
Okay.
Okay.
cool then. Thanks, guys.
Thanks. Bye.
Bye.